So in today's session, we'll primarily be finding out the greatest values of two different concepts. So in today's video, we'll be concentrating on the chapter of combination as well as the chapter on binomial theorem. So let's first start with combination. The exercise is to find the greatest value of NCR. So let's say we have been given a lot of values, NC0, NC0, NC1, NC2 up to NCn, and we need to find out the greatest value of NCR. So let's say we have been given NC naught and a lot of values and NCn, and we need to find the greatest value of NCR that we have. Now, NCR and NCR by NCR minus 1, as we have discussed before, solving this fraction, we get n minus r plus 1 by r. So naturally, NCR by NCR minus 1 will be greater than, equal to, or less than according as n minus 1 plus n minus r plus 1 by r is greater than, equal to, or less than 1. So if this numerator is greater than the denominator, then this numerator will be greater than the denominator, which means NCR will be greater than NCR minus 1. Again, if the numerator is less than the denominator, then this numerator will be less than this denominator, and then NCR will be less than NCR minus 1. So which of these two is greater than the other depends on the value of this fraction. Now I've simplified the value of this fraction. So n minus r plus 1 by r greater than, equal to, less than 1. If I simplify it, the condition boils down to r less than, equal to, greater than n plus 1 c2. Please note that there has been an alteration in the sign or the direction of the less than, equal to, greater than signs. So when you do this solution, please check that you have the correct direction. Now, let's say we have a situation where n is even, say n equal to 2m. This 2m denotes the fact that n is an even integer. Now, if n equal to 2m, then going by this assumption, n plus 1 by 2 is equal to 2m plus 1 by 2. I replace n equal to 2m. So 2m plus 1 by 2, which again boils down to m plus half. Why I found this is, this n plus 1 by 2 is essentially from this portion. So now the relation boils down between r and m plus half. So if r is less than m plus half, then the numerator will be greater than the denominator. That is how I use the condition. Now, again, note that m is essentially a positive integer. It's like 1, 2, 3, 4, 5 of sorts. So if r is less than, but this entire m plus half, this becomes a fraction, because if m is a number, or if m is an integer, if it's 1, 2, 3, 4, 5, and then there's a half added to it, then this entire m plus half becomes a fraction. But r can only take integral values. So if m needs to be less than, if r needs to be less than m plus half, then it will be m minus 1. And if r needs to be greater than m plus half, then it needs to be m plus 1. It can't be m plus half anywhere. R cannot take the value m plus half. So what we have is, till the value NCm is achieved, all the times NC0 will be less than NC1. NC1 will be less than NC2. Because you see, if R is less than m plus half, then we have NCR minus 1 is less than NCR, because the direction is on the opposite side. So when R is less than this part, then the numerator is greater than the denominator. So we have NC1 is greater than NC0. NC2 is greater than NC1. So we have the direction which says NC0 less than NC1, less than, going till NCm minus 1 and till NCm, because it hasn't achieved this m plus half. It's still, when r is assuming the value m, it's still less than m plus half. As soon as the r value achieves this m plus 1 value, it becomes greater than m plus half. So the direction reverses. So when we have r is equal to m plus 1, that means r is greater than m plus half. In that situation, the sign, as you can see, it reverses direction. I'm not putting this value because it might sound like it might look like I've put an equal to sign. So as you see, the direction of the equal to, the less than, greater than direction, and the less than, greater than direction on this side is different, because it has crossed the threshold value of m plus half here. So the direction has changed, and then the direction again continues to be the same till the end. So we have NC naught less than NC1, less than NCM minus 1, less than NCM, greater than NCM plus 1, greater than NCM plus 2, up till NC2M. So in this case, NCM is the largest value. And putting the values, we have NCM, M is equal to N by 2. So we have the value. You can find out the values. Of course, if you find any problems, then you can, of course, contact me. The next case is if n is odd, say n equal to 2m plus 1. So we are considering the situation where n is odd. Now we are again replacing the value n equal to 2m plus 1, and this time we get the value m equal to 1. So what you see is still the value NCM, there's no problem. It follows the same logic as the previous part. But in the situation where r equal to n plus 1, if r is equal to n plus 1, then the numerator and the denominator of NCR by NCR minus 1, the numerator equals the denominator, if you checked before. So what happens is there's an equal to sign in this section. The value of NCM and NCM plus 1 is essentially same. So we have NC naught less than NC1, less than NC2, which continues still less than NCM in fact. Then it becomes equal to NCM plus 1, and then it again starts to fall. So it goes on till NCM equals NCM plus 1, and then it again starts falling. So here we have two values which are greatest in magnitude. So again we put the expressions, and if you notice one thing, they have equal value because they are equal to each other. So finding the value of 1 will suffice. So that is the way in which we find the greatest value of NCR. The next part, we'll concentrate on binomial theorem. So here we find the greatest value, greatest term in fact, in expansion of a plus x whole to the power a. So as you know, tr plus 1 is the r plus 1th term and tr is the rth term. So we put the values that we knew from beforehand, and this NCR minus 1, it's just what we discussed before, n minus r plus 1 by r. And if we cancel out the values on this side, so there's x to the power r minus 1, and there's x to the power r here, so it gets cancelled. Again, a to the power n minus r, and we have a to the power n minus r plus 1, so this a gets cancelled and there's an extra a, so a remains. So we have n minus r plus 1 by r into x by a. Sorry, we use the same logic that we did in case of the combination part. So tr plus 1 is greater than, equal to, or less than tr, according as, again we use this part of the expression. So we solve this expression in what I did essentially was I put it equal to, greater than, equal to, less than 1. Then I multiplied the denominator on both sides. So I got nx minus rx plus x greater than, equal to, less than ar, and I solved and I got the value of r from this, because r is essentially the value that it will consider. So that's how I got this value. Again, similar to previous case, we have two cases here. So here again we have two cases, but the difference is in the previous case we had odd and even situations, but here we'll have a different form of approach. So when, let's say, n plus 1 by x plus a is m, where m is a positive integer, so it's a positive whole number. So when r achieves the whole number value, it becomes equal to that number. This is like case 2 of the previous situation that we considered. This is a value that r can achieve. Basically, in both the cases, we take a situation where the number or the threshold value is a value that r can achieve, and a threshold value that r cannot achieve. So whenever we consider a situation where the threshold value can be achieved, we have two situations where we have two, basically we have two greatest magnitudes, and that is exactly the same procedure that we followed. So t1 less than t2 less than t3 less than tm, it continues. Then since this threshold value of m plus m can be achieved, we have an equal to sign here, and then again the sign reverses to tm plus 1 greater than tm plus 2 greater than tm plus 3, and it goes on till tm plus 1. Case 2 is a value where the threshold value cannot be achieved by r. So what happens is this n plus 1 by x plus a, it is m plus some positive proper fraction. So this is essentially the entire value becomes a positive improper fraction, but it still becomes a fraction. So R cannot achieve an improper fraction value. So this is actually a threshold value that R cannot achieve. So essentially we have a situation where we have only one single value of greatest integer. So T1 less than T2 less than T3 less than up to Tm less than Tn plus 1, then the sign reverses, because until and unless R achieves the value which is given by this expression, it cannot have the equal to sign. But R cannot assume a value which is a positive integer plus a positive proper fraction. R cannot achieve a value which is an improper fraction. So this equal to sign will never hold. This equal to R cannot ever hold, but R can only be equal to this, and that is the only situation where we can have an equal to sign here. Since that is impossible, we do not have an equal to sign in this expression, and we end up with T1 less than T2 less than T3 up to less than Tm less than Tm plus 1 greater than Tm plus 2 greater than Tm plus 3 greater than, and then we have the last expression as Tn plus 1. So that is the significance of the greatest value. And as you can see from this exercise, the chapter of combination and the chapter of binomial theorem are very much interlinked together. So when you study these two chapters, try to study these two chapters simultaneously.